Cool to be here. So, we are continuing on Stateful Orchestration. I call it Stateful Orchestration 2.0 because it's effectively the extension of the previous episode. We had a bunch of slides that we did not get to be honest, as planned last time, so now we have expanded content. First and foremost, I would like to announce, mention, say, this meetup is, I would say, 3-something years old. I started it when COVID lockdowns began, when I realized it's going to be super boring, so we might as well talk to each other. And I was always hoping for some architect's corner route, where we would have a bunch of smart people who know their stuff, and people would come to us and talk, sometimes on air, recorded, sometimes off the record, about their problems, and we can just discuss them together. I always say, please interrupt me, please don't be shy. So it works to a certain degree, but it's mostly me talking. So thankfully it's changing for real today, because this episode is co-hosted by Ivan. We work together, we spend tons of time together. Most of these slides are to a large degree a distillation of our shared ideas. Some of them, Ivan, are truly yours. I mean, I take some credit for thinking of them for many, many years, but I assume you did too, as evidently is the case. So yeah, I'm hoping for more stuff like this. Last episode was called Stateful Orchestration. Today I'm also adding the term durable execution. That's a new term, and as it always happens with new terms, it's not clear if it will stick. It may change its meaning, but personally, I like durable execution, because that's exactly what I believe. The English language is so good at making good terms, I have to say. Other languages I speak are not as good. In English, you can just have a good combination of words and have it stick. Durable execution, to me, if I don't know what it means, would imply that once you start running your code, you can count on the way it runs, which is exactly what we need from code in the 21st century, especially for the broadest possible class of problems where it has to do with data, with consistency, with no conflicts, and if it's in a distributed setting, when multiple machines are involved, they can always die in unpredictable order, and you may need to roll back some transactions, redo things from scratch. So that's exactly the code you would love to run durably, so that the engineer does not have to worry about all these corner cases. That's exactly the black hole of complexity. So tons of code, not all of it. There are tons of engineering tasks that do not require durable execution. But the more I dive into SysDesigns, the more I'm convinced this is where the black hole of complexity is. This is what needs to be improved. So we're going to be making bold claims today. And I wrote a bunch of blog posts a few months ago. There's a blog post I'm going to link to. It's called What Colors Your Function? And it's about moving from synchronous functions to asynchronous functions, and eventually arriving at what we all use today as async await. So behind the scenes, async await is not just the paradigm of is not just an extension of the library, right? It's the new way of writing code. It requires language support and framework support, because functions that are asynchronous, async functions, they require a whole different runtime. You can also call them resumable functions or stoppable functions. They are stackless by design. Green threads are not the same as OS kernel threads. And somehow async await was such a genius breakthrough. It saved us from the callback hell. It saved us from complex indentations all the way to the one side of the screen. So thankfully, we all speak async await, and it's a first-class citizen, and we use it all the time. My claim, or our claim, is that durable execution can be something that we can all just move to, much like we moved to async await, and never look back and produce better code, safer code, more reliable code, more bug-free code, faster. And yeah, let's just keep going. For the first time on this episode, on this meetup, for the first time for real, I'm going to outline the problem first and then solve it as if it's a pitch deck, because why not? It's like a white paper, like part of it, half of it, after all. So the problem is that when distributed data enters the picture, that's the part of a large-scale industrial software design where the rate at which the technical debt grows is just insane. Like you could literally, I witnessed cases where a team of 10 plus people are working for a year on something that in isolation, if you're allowed a downtime of like 2 hours, in isolation, 3 people would do in a week. Because all these checks, all these corrections, migrating from one database to the other, making sure you run all the dry runs, making sure you never lose the data, making sure all the data residency, data locality rules are respected, so difficult. So when data is distributed and have to respect certain invariants, tech debt grows exponentially, feature delivery pace suffers. Instead of launching 10 features a year, the company launches 1 or 2. And I claim that it's easily the area where like 10x more time in astronomical units and 100x more time in developer years is just wasted. And I'm going to present the case. We're going to present the case that this can be improved by using proper approaches, frameworks, techniques, whatever you call it, it's coming. The solution is to prevent the tech debt from creeping into where it should not exist to begin with. And in simple terms, the claim is that if you look at the code base at each large company, well, in most large companies, maybe there are singular exceptions, the problem is that lots of different layers of code tend to get intertwined as spaghetti code. So you have business logic code that is super trivial, but you also have database level code, transactions, rollbacks, persistence, sagas, and orchestration. And on the one hand, every single senior plus engineer can reason about data integrity easily. On the other hand, instead of enabling them to do it most of the time, they are happy to do it maybe one day a quarter, which is something we can improve. So the plan is to have this programming paradigm and the framework to execute the code written in this paradigm, where the whole idea of where the code is executed is abstracted away from the developer. I like the analogy to async functions. So if you have an async function, you're not supposed to think about which kernel thread executes this function. You can do async, you can do and you do async await in Node.js, which is inherently single-threaded. So it emulates multi-thread environments, and you're not supposed to think about which thread runs the code. You just know that the guarantees the environment provides you with, they are respected. Let's make the step of comparable magnitude in the world of distributed computation. If you need some piece of code to absolutely run exactly once, we'll get to that. And as soon as you need this guarantee, unless you have a durable execution framework, you are responsible for making sure you store the state somewhere, potentially restore it from a different machine if this machine dies, check any potency tokens because you have no idea if before dying it went through part of this code or whatnot. That's all difficult, that's all expensive. Let's take this duty away from the developer and let's do it on the framework level. This includes respecting data invariants. My claim is that the moment you as a developer have to think about how to compensate for a partially failed transaction, be it a database transaction or logical transaction, like consume some Kafka event, publish something to Rabbit, and confirm to Kafka that this event was consumed. Once you have to think about what if it fails midway, that's too late. If in a good framework, in a well-designed architecture of this framework, the engineer should never ever have to think about it. It just works. It just works. TM, my favorite term. A bunch of links, I'll just skip through them. The blog post I mentioned, what covers your function, blog posts we wrote before, previous episode, and some pictures I totally love from back from 2015. Ironically, most of the ideas we're going to present today are very similar to what we talked about 10 years ago, except the part where back then I was a huge fan of event sourcing. Event sourcing as a single source of truth, as in the single totally ordered stream of events, which can be applied specifically in this order. So all the events happened in a certain order. For every 2 events, you could say which one happened before the other one. And I still think it's a good paradigm, but total order implies you have to be able to process things sequentially, which may just be too many per second for many systems. And it's embarrassing to try to do everything in a totally ordered fashion because most operations are perfectly parallelizable. Think of Google Docs. Like there's no point for every single person who's editing a Google Doc to have their own unique sequence ID and throughout the entirety of Google Docs. You can just have a order of things per document, right? But cross documents you don't need to. You may argue that for stuff like sharing settings per organization makes sense. But if you're editing a Google Doc for yourself in America and someone else is doing it in Australia in a totally different org, there's no need for them to be even potentially colliding. Contention, as in lock-in that blocks other parts of the code, is the only expensive part in SysDesign, more or less. So whenever we can avoid contention, we should avoid contention. I should mention that there is quite some existing work, of which I would highlight two things. One is that we have a bunch of frameworks that are starting to be quite mature at running these ideas. Most importantly, that is Temporal and Cadence. Temporal is open source and free to try. Do try it, it's tons of fun. And I have to publicly apologize to Max Fatiev, who's the CEO and founder of Temporal, because I was incorrectly stating last time that Temporal is enterprise grade. No, it's open source under MIT license, which is my favorite license, so be sure to give it a shot. In addition to Temporal, I also think it's worth highlighting that with all my mixed attitude towards Web3, quite a few, like if you cut out the fluff, if you cut out all the fanciness, the quality of high-tier ideas in the Web3 space is getting better year by year. And I think today quite a few ideas are mature enough. You can spin up your own blockchain, you can have your own proof of stake, you can have your own orchestration based on custom logic, and it just works. And this, I have to say that this phrase in the code, that's taken in quotes here, because that you have many computers, many nodes, and they all compute the same function. I first heard it from the Web3 community, and this is a really good way to think about it. And so the claim is that when it comes to durable execution, in many aspects, for many local-ish tasks, this problem is solved in the Web3 community. Maybe not in the most effective way for your company or your enterprise to adopt it, but it's like mathematically speaking, we have more solutions today than we had 5 years ago. And both of us, Ivan and me, would like to highlight that the solution we're suggesting can totally work on non-standard, non-computer, non-server environments. I always think of mobile phones first. Imagine you could just buy a bunch of second-hand phones and just run your software on that. Like literally, instead of paying Amazon, go to Craigslist, buy a bunch of Androids, and that's your backend. Like buy SIM cards, use some VPN service that you pay for yourself from your company, send them to different parts of the world, and you're good. It just runs. And Ivan introduced me to the idea that you can run code in web browsers. Like people can just open a web browser and act as the supplementary backend node for a service, which is super cool if you think about it. So yeah, this should at least be mentioned, I think. And here's the list of the bold claims we will make. Claim number 1 is that moving to node-agnostic programming is ultimately good. I touched on this briefly at the beginning. The whole point is that the developers as a community should be quite easy to retrain to learn how to write the code in a way that does not make developers think about which exactly is the node, the physical machine that runs this code. If the frameworks are ultimately designed in the right way, if your code goes from one node to another between some literally if else, but more likely between some awaits, that is perfectly fine for you as long as the framework guarantees the execution is durable. So I do, like in the previous episode, we talked about the requirements for the developers to write such code. I don't think we should go into these details too much, but it's actually not hard. You just need to write the code that is not using randomness, because it should always use pseudo-randomness, not depend on local node, local kernel, local OS. Never use local time, of course. Use some pseudo time. It's not too many things to worry about. The only confusing part is if you need to iterate through like a hash map. The order of iteration could be platform agnostic, but come on, those are minor details, and it's easy to work around them. Bold claim number 2 is that what is called event-based development or event-driven development today is just broken. People talk about it, people love it, because it sounds so good on a high level. You have multiple teams in a big company, and someone says, oh, you guys have events. Can we consume these events? Because something in our business logic should be dependent on what happens on your side. We can just pull your database. We can send you a query every second. But it's so ineffective and slow. Why don't you publish this event somewhere to a PubSub bus, and we can consume it? And it's so easy to sell people on the idea that PubSub buses are good. And don't get me wrong, there are tons of good use cases of PubSub buses. They take care of what is called the back pressure problem. If one side produces events faster than the other side can consume them, the other side is not overloaded. It's the bus that is handling this as a buffer. Then you have this wonderful concept of decoupling consumers from producers. So by adding a new consumer, you cannot possibly affect the producer, which is super wonderful, fantastic, it's cool. Let me see if I can quickly hide non-video participants. Yeah, that's better. So it's awesome with PubSub because you can decouple consumers and producers, and this makes the system far more durable in the long run in terms of development stuff, which is cool. And even though I have this mixed attitude towards Kafka, because I think it imposed tons of suboptimal decisions into the brains of millions of programmers around the globe, Kafka is still a good primitive. And if you understand topics and partitions and confirmations and consumer groups natively, which is not hard really, you can build tons of good software. My beef with modern day event-based development is that people think it solves all the problems, but it's just starting to solve them. Try talking to a Kafka expert, to a random Kafka expert about schema evolution. What do you do if your data changes in format? How do you make sure your downstream consumers are not confused by old formats? And that's easily what teams can spend years fixing in a big company because there are no frameworks for that. I mean, frameworks begin to exist, but it's again, organizationally, it's a disaster to orchestrate properly. Tons of careers, tons of promotions, like people become staffs and senior staffs. But in terms of, is it effective enough at the world scale? I would say as of 2024, nowhere near. And then I'm going to claim that we can go back. That's going to be the third bold claim. We may well go back to the roots, because the original ideas of object-oriented programming and domain-driven design, OOP and DDD, they can be applied really well if you rethink how they apply to modern-day principles. So we have objects and singletons. That is actually what OOP is about. Like I can rant about this for hours, but fundamentally OOP is not public protected private, and OOP is not inheritance, polymorphism, encapsulation. OOP is about objects talking to each other through messages. And the original ideas of OOP, if you begin thinking of objects as something that lives in the local universe that is across machines, that exists in some virtual space that is guaranteed to keep these objects in a correct state, as opposed to some memory locations that are totally lost if the machine is dead. If you think of objects and data singletons, a lot of things make sense. If you think of types as invariants to respect on these objects, it's clear how to evolve them. And if you literally think that all the business logic code is just how to evolve these objects over time, how they send messages to one another, how the system responds to external commands, if the business logic is 95% of the code and not like 5% today, scattered between database persistence layers and sagas and compensating transactions, that's a better world, which I believe we can and should get to. I will not go too much in details here. All these bullet points are covered in detail in the previous episode, literally. But I would love to point out that if any of these bold thingies here interest you, if you struggle to convince yourself to read more about them, hopefully after today's episode, you can skip this for now. But it's going to make a lot more sense why these things are important after you listen to today's episode, which means if you like a top-down guy or gal, just go ahead. If you're a bottom-up person, might as well do the homework first. Your call. So, the most interesting part is that, as the old saying goes, the new is the well-forgotten old. All of us these days are familiar with Git flows. Like you can do branches, right? You can merge them back in, you can fast forward, something you have conflict, sometimes conflicts can be resolved automatically, sometimes they require manual merges. We also have GitHub Actions and stuff like that, like hooks too. The claim is that you can version data objects, data singletons, data instances through the process that is very similar to how your Git objects evolve. Like imagine hypothetically your business entity, such as a Google Doc, can be thought of as a repository on Git. And every single mutation to this document, or every single comment as well, like sharing technique, highlight or whatnot, is a commit. It's a diff here. And suddenly a lot of things make sense. If you and I work on a document concurrently, we just send our own commits, every single keystroke can be thought of as I make a change in my local branch, and then I try to merge it into the main branch. If there's a conflict, there's a conflict. If there's no conflict, we merge it. So this logic holds. And the claim is that you can apply this logic and go places. Another term we can borrow from the past is optimistic lock-in. I'm going to use this analogy again from the previous episode. I think, Ivan, you told me about this. It's a really good... So TLDR, don't use mutexes. Mutexes are slow. Mutexes are extremely slow because they were meant to be used by in the old times, far before async await. Mutexes, if you lock a mutex, you are pretty much assuming that you have a high contextual environment. So you have to wait until it's your turn. And this logic of who waits and who goes next is being outsourced to the kernel. And kernel calls are expensive. It's at least 1600 CPU cycles. Maybe it's better these days, but still it's an expensive call. Whereas green threads are faster and lighter because they do not go to the kernel. They live in the user space. So if you use like a lock-free queue, by design, lock-free queue is faster. Unless you're in super high contextual environment, but it's not what we're talking about right now. So optimistic lock-in can be thought of as a roundabout. If two roads cross, if it's a crossroads, if it's a roundabout, you just slow down a bit and you go further. If it's a traffic light, you need to wait for your green light. So if the traffic light is operated by the OS kernel, that is slower. In many cases, if you just predict that most of the time the roundabout is empty, it's faster to use lock-free data structures. I would like to go further and talk about the concept of STM, software transactional memory, which I heard of many years ago and never used directly until finally it's time. It's the idea that instead of trying to be pessimistic and lock everything, you can just run your transaction once in memory, but every single mutation you make, you make a note of which version of the object you accessed in memory you accessed. So which version you worked with. And then by the end, you check the versions again. If all the versions you touched have not changed, then you are guaranteed to have not committed any conflicts. So you only commit the transaction if no versions have ever conflicted. And if they did conflict, then you need to redo it maybe again, like try a few more times, and then if you failed, you lock stuff. That's the idea behind STM. And I also never like this idea of locking in a distributed setting. Honestly, I think distributed locks are one of the worst ideas ever, because if you lock something in a distributed setting and your machine dies, you inevitably end up having to have some timeouts. You could say that machines don't die frequently, so timeouts can be large, like not milliseconds, but maybe like 10, 15 seconds or a minute. But then again, if the machine died and the lock is held, at some point the lock is released, and this is not an atomic operation that the lock is released, and people can, like other nodes can start conflicting, you need to rerun the literal elections. That's painful. Any design that does not depend on distributed locks is better. And one example I love to use here, I like to think I invented it, but I'm pretty sure I'm not the first person to talk about this, is like if it's one machine and multiple CPUs, this concurrency, it's already difficult, but it can be compared to Newtonian physics. You're operating at sub light speeds, at normal human comprehensible speeds, and everything is close to each other. It's still like the speed of light is large enough so that all the bits of data, all the pieces of data are within nanoseconds of reach. But imagine your distributed system is on a planetary scale. Some servers are on Earth, some are on Mars, some are orbiting whatever, Saturn, asteroid belt. So the very idea of which action happened before another action makes no sense. Because today, Earth and Mars are on one side of the sun, tomorrow they are on the opposite sides, and the asteroid can be closer to Earth or Mars or whatnot. So any assumptions on the order in which the signal travels from A to B, it just doesn't hold. I mean, the triangle equation still holds, but latencies and lags would be remarkably random. The Web3 community has solved this. With checksums and validation, this works. But in standard-ish reasoning of distributed systems, once you start talking about cross-region replication, things start to break. Even though you can have a raft cluster, for instance, spanning continents, most raft implementations do not recommend it because they can and will break. So it's still an unsolved problem to a large degree. Okay, I'm talking too much about this. Bullet point number 3, we will borrow some ideas on functional programming. Not the monads, don't worry, but at least immutability and the idea that you can just combine operations as long as the object supports these operations to be combined in any order. If they're commutative, you can do a lot more. And of course, proper OOP, I already rented that it's about objects talking to each other and not about buzzwords. This is a 30,000 feet view of the solution. First of all the data lives outside the realm of individual machines or nodes, which means, physically speaking, there's no single source of truth for anything. So continue with the Google Docs analogy, the question of which machine has the true state of this document makes no sense. And logically speaking, it cannot make sense, because if there's a single source of truth located within a particular machine, this machine can die, and then the document is lost. So in a perfect world, the single source of truth exists logically, as in you can reconstruct the document, but there's no single physical entity which contains the latest state. Then we need to talk about business logic. When I say the business logic, it's synonymous with code. That's what the teams working on features need to write. So to me, business logic code is complemented by non-business logic code, which is all this persistence logic, sagas, locks, distributed magic, consensus. So let's group all these under non-business logic code and focus on business logic code. So my claim is that the business logic code should be totally isolated from persistence. You can work with any object, any data entity, any data singleton, and you can, speaking in Git flow terms, you can have a branch, cut the branch of the current main state of this object, or whatever previous state, doesn't have to be main. You can cut a branch from anywhere. You can add commits there, literally, whatever legal mutations can happen, legal as in like type safe, type aware, you can apply them. And then if you want your changes to make it to the main branch, you send a pull request. And if the pull request is not conflicting with the main branch, it just merged. If there are conflicts, sometimes you're lucky and they can be resolved automatically. Sometimes you need to retry your transaction, which is also fine. So my point is that the business logic should focus on objects, sending each other fork requests, branch requests, and merge requests, and that's it. And then, of course, the schema is part of the code, because if you do it right, evolving the schema, the issue with schema evolution is that once you evolve the schema, the old data is still there in the old format. But if all your data is data singletons, then effectively when you change the schema, it's a linter level, static check of your code. Hey, you have this new format of the object. Do you have a constructor for this object from its old format into its new format? If you don't have this constructor, you cannot evolve. If it's a trivial constructor, assume you have it, unless you need to change something manually. And if you do have this constructor, then at which point in time this internal object representation changes from old to new, that's none of your concern as a developer. The framework takes care of this. You just operate with this object. Once we evolve the schema, the blockchain folks have nailed it. We have blocks on the blockchain, but if you need to change the internal logic of the blockchain, it's the entire block. So you have this before and after when you need to change from old to new. So if you have a schema evolution event, schema evolution command, you change everything. It has to pass linter and static checks, and then in an instant you assume every single object is presented to you in the new format. When it is evolved, it's none of your concern. That's what the framework does for you. And the last part is, we thought about this for a long time, but it looks like it's far easier to assume some global lineage exists, some global totally ordered stream of what is usually called epochs, like 1, 2, 3. I like to think of them as something that happens, let's say, 10 times a second, like not too slow, not too fast. And by no means I'm saying that every mutation to every object has to be part of this, has to have assigned its own sequence number. But since we cannot use like local time, because local time is unreliable in distributed settings, let's just assume we have this idea that the user request from the outer world was sent at this epoch number, and the response was sent at this epoch number. If it's 10 per second, 2, 3, 4 is perfectly fine for big, expensive operations. That's effectively for large-scale merge conflict resolution if they span multiple entities. Yes, Alex.
Can you please come back and cover one more time the schema is part of the code? I probably missed this like the schema. What does it cover? Does it cover like the whole code? And whenever you make a change, you make like a schema transition operation for it? Or yeah, can you please cover this one again?
If it's a SQL database, RDBMS, schema is just what columns you have and their type.
So we are talking about data storage, not execution code or.
Right. We're not talking about execution yet.
Okay,
So,
cool.
but
Then it's fine.
but it's still a good question. So if you're talking about SQL schemas, the schema is just a schema of the data. There's no way to put the code into the SQL schema. You could have some logic in like stored procedures, but we're not going there. If you're talking about document stores like Mongo, you could say that you store everything in JSONs, and the schema is the JSON schema for every single object. The point we're making is that you can go further. You can say that the business logic code, when stripped of all the persistence, intricacies, and marshalling and whatnot, the business logic code is usually comparable in simplicity and readability to the schema itself. It's actually one of the strongest claims of functional programming, that if you have a strong type system, you can guess what the function does by its signature. It's just clear. So if your schema is like this user has first name and last name and the country of origin or country of residence or whatnot, the business logic is single digit number of lines to like change your name, for example. That's what the code is data. That's what I mean by saying that the schema is part of the code. You change the schema, and converting old to new is just a separate constructor type, and it's usually just a few lines of code, and you just push it into the main lineage. It gets this global lineage clock, global like epoch ID, that at this epoch number, we move to a new schema, and the magic works itself. Thanks for the question. So yeah, then data singletons, I covered this briefly, but I never went into full details. So the data singleton can be a single, like literally a single object in the entire business, in the entire universe. But to me, if it's a map of some ID into this object type, it's also a data singleton. You can think of them as multiple data singletons. It's like a factory of Git repositories, if you wish. I don't like to think of them as branches, but you can think of them as branches too. You can say that you have this repository called documents, and every single document is its own branch name. And then if you want to change it, you have this document ID dash something as a dev branch, and then you merge it into document ID. Like, it's immaterial from the data integrity standpoint. The point is that on the level of each individual data object, that's where this partial order happens. That's where the vector clock of the entire universe has a new component. Whereas across different data singletons, ideally most transactions have to do with only one data object, which makes things simple. Once you need to perform atomic operations on multiple data objects, eventually you're going to need to lock them to modify them concurrently, maintaining invariance, and that's where the framework kicks in. My favorite example here, very indicative, is if you have users within different like teams, And when you add users to teams or remove users from teams, it's all team specific. That's it. Like, think of a JSON blob list of users within a team as a single Git repository. Trivial. Add line, remove line. But if you move the user from one team to the other, it should be synchronized between two teams. There could be an invariant that a team can have no more than 10 people. Like, you need to pay more to upgrade your plan and stuff like that. So this is where you need to effectively make a simultaneous merge request into two repositories. So if you have this map of team ID into this JSON blob, on the one hand you have partial order, because between two teams you don't care about the order of mutations. But when you need to merge the conflict, that's where the magic happens. That's where the knot ties. Now we're getting into the weeds slowly. So each data singleton has one or more atomically mutated perpetual slices. I'm not sure the term is good, but so far it's the best we have for you. You can think of, as I said before, you can just think of each object state as a single JSON object in a single Git repository. And yes, it would be a single vector clock component, single partial order key, partial order time key. But you can have more than one logical orders associated with the same object. It is because sometimes different parts of the object have different requirements on how conflict-free they are. So we get to CRDTs. Basically, some data types are by design non-conflicting. For example, counters. If you want to keep a counter of how many times you access this object, the mutation is increment the counter. And counter increment cannot conflict with other counter increments. It's pretty easy to build a system that is always keeping the total counter number correct. But if you need to perform something that potentially conflicts with other operations, where the conflict can happen, you need to have conflict resolution. The point is, a single object, a single data singleton, can have multiple components of these vector clocks, so multiple partially ordered components that are not tied directly to one another, specifically because this allows you to keep some of them more conflict-free. It all has to do with less contention, so more effective parallelism factor. We'll get to this on an example in a moment. And of course, once all this is done, business logic is effectively a distributed workflow. That is, if you read anything about Temporal or Cadence, it would make sense to you. If you read our blog post on maroon functions, it would make sense to you. It's effectively this async await style code, but because it is distributed friendly, so all pseudo-random, no local stuff, it can be executed and resumed on a different machine as needed if machines die. Now we're getting into the weeds of perpetual slices. We're gonna claim that you can have infinite variability with using only 3 primitive data types, or type classes, type universes. You can have CRDTs, which I just briefly talked about. CRDTs stand for conflict-free replicated data types. I always confuse these things. Yeah, so that's counters that are guaranteed to be maintained correctly regardless of in which order you apply their deltas. Our canonical example, if I were to go too academically, I would say that Martin Kleppmann keeps writing papers about or reviewing papers on CRDT JSONs. Like, to me, it makes very little sense in practice, because whatever rules you come up with, if something has a conflict, you cannot resolve it without resolving the conflict. So you can come up with different ideas, different clever ideas on what you can do in a conflict-free setting, but it's still a logical question, not a mathematical question. It's like a business logic question. But I want to point out there are more types of CRDTs that are truly CRDTs, such as insert-only sets. If you can apply any set of mutations in any order and get the same result, you can have a CRDT. That's why counters are CRDT. Reorder all the deltas. If it's all integers, if you don't worry about overflows and precision details, in any increment in any order, give the same result. If you have a set into which you can insert stuff, such as numbers or strings or whatnot, IDs of some type. If you can only insert, the order does not matter. If you can remove, then you can insert A, remove A, insert A, and suddenly the order matters. if you rearrange the order, you may end up with a different final state. If the final operation was add, it must be there. But if you flip add and remove, you're in trouble. So insert remove set is not a CRDT, but insert only is a CRDT. And that this can be leveraged quite often. For example, I would argue that every single log collecting operation must be a CRDT. It's append only, but the order in which you append the entries doesn't really matter. If it's stuff like Sentry, like front-end level login or back-end level login, journaling for further debugging, that's a CRDT. It should not possibly be a conflicting operation to insert something into the log file. The order of rows may change, but logically you don't care. After CRDTs, you have non-log-free types. That's effectively where conflicts may happen. And that's where the analogy with, some text is incomplete here. I apologize. This is where the conflicts might happen. So in practice, that's effectively like you're taking the branch, you're forking a branch of the main branch, then you can change it, make local commits, and pray or hope that the merge into the main branch will succeed. In database terms, this is called MVCC, multi-version concurrency control, standard term. You have multiple versions so that other parts of code could see your version without knowing full well that it's going to be final or even existent on the global lineage of the lifetime of the object. It could never get committed. We're not going into details, but the point is you have this non-master branch, which may or may not be part of master sometime soon. On super low level kernel level programming, the term is copy on write. So like you copy some memory, but you don't copy it until you modify it. Once you start modifying it, you have a copy made by the kernel for you. Like logically the same thing. And then you have the merge conflict that can emerge. And then there is some merge logic. The part that is not written in the slides is that potentially you can even use your business logic programming language to build the logic of new custom types. But let's assume for now they're just standard built-in types. Like I always think of the default non-log-free type as something that is versioned. So you have some version number of the object. And the only operation you can do is compare and swap, atomic swap, only if the version you're trying to override the current version with is n+1. So clearly, if you're the only person trying to make modifications, you can go from version 1 to version 2, from 100 to 101. But if you claim you have a version 103, but it's already 107, sorry, you're late. Try again. That's the basic type of conflict-aware type. If I modified since as the header in HTTP in REST is another standard way to refer to this. I like compare and swap because it's an assembly instruction. Like to me, it's more natural to talk about low-level stuff. But if I modified since as a standard header, you can Google it. That means exactly this. And we are introducing the third primitive data type, which I call loosely ordered queues. Effectively, this is reserved for what cannot fail as a conflict, but some wiggle room for order exists. And that's the primitive that makes it all fit together. The idea is that some object or some primitive slice of the object can be a loosely ordered queue of some commands, events, messages, doesn't matter. And any other member function, so to speak, of this object can push to this queue. Whatever it pushes becomes available for processing on the next system framework level global epoch. And within the epoch, the order in which the pushed events are pushed is determined by the framework as the current epoch ends. So in order for it to be conflict-free, what you trade for it, what you lose, is the fact that whatever you inserted in epoch 1,000,003, all of this will be available exactly once because there's idempotency. Every single message you inserted will be there exactly once to be processed at epoch 1,000,004, the next one. But the order, sorry, we have no idea. It's going to be something, it's going to be fixed by the time the epoch is done, but it's not something you can rely on. So that's your trick to like introduce delayed execution. In JavaScript, the analog would be next stick. If you want to yield control and get back, you say next stick and do this run this code. So you give control to the environment and then you get called back. You cannot know exactly in what else has been performed in parallel, but by this time you can run your code. That's pretty much exactly what loosely ordered queues are. If it's too complex, I hope we get back there eventually. Oh yeah, so I actually covered this. Push data becomes available as the next epoch begins. Within the current epoch, the order is not deterministic by design. You could argue that the read your own rights guarantee holds. So if the same code made like 3 pushes, 3 inserts into this queue, these 3 inserts would be in the order that happened, in which they happened. But if other daemons, maroon fibers, asynchronous workflows made pushes to this queue, sorry, no guarantees. Even though, of course, there is idempotency for exactly once. And yeah, to process these events, you need to wait for at least one epoch because the ordering should happen. It's the same idea as with log-free queues, effectively. Right. I think we briefly talked about this in the context of traffic lights versus roundabouts. The idea is that whether we like it or not, fundamentally, on the framework level, we should have the means to lock some object. So it's, in a way, up to this point, we always said, hey, the Git analogy holds. You can always cut a branch, you can always try to merge it, and like your local commits, if they don't have conflicts with other code, it's okay. What I'm saying right now is that it is possible to do distributed lock. It's not going to be distributed held on a particular machine. It's not tied to a machine. It's tied to like a maroon thread, which is a green thread idea taken to the distributed framework. It's locked by a particular piece of logic of code, the execution of which is not tied to a physical machine. So you can assume it is guaranteed to be fully run until the end. So it's safe, as in there's no need for you as the user to think of corner cases. What if it fails? It will not fail. It could run for longer than you expect if you like overload it on machines dying, full outage, but it will not fail. It is highly not recommended to use this lock-in, but sometimes you may have to. And yeah, that's part of the framework. And the trick here is that you can lock for at most one epoch. That's another trick we think is making things a lot safer. If you have epochs of like 10 per second, so 100 milliseconds each, you can go too bad if you lock stuff. I hardly discourage production code from doing that, but if your code is built in a clever way, you would first do optimistic locking, as in let's hope there are no conflicts. Then you would use this loosely ordered queue, which is where the objects, the commands would be assigned some order on one epoch, and then the next epoch your code can just apply those mutations in order. So the conflicts, if any, would be clear. And only then, if these two failed, you can do a proper lock-in. In fact, it might sound more difficult, but trust me, it's far easier than sagas and orchestrating frameworks like command. It's a bit like learning how to use async await and like waiting on multiple objects. It's a skill, but it's fast to learn. And now, when it comes to writing business logic, which I believe is all the code that the user should write, because the framework takes care of the rest. That's again the idea borrowed from the early days of OOP, object-oriented programming, that every data singleton has its own small inbound message queue tied to it, so that the framework can guarantee that incoming commands are processed sequentially. You can assume that there's no concurrency unless you introduce it. I mean, you can do async await, right? You're totally allowed to make external calls, in which case you can end up in a parallel world, which is perfectly fine. That's what you want. But you can assume that, much like in JavaScript, as soon as you do not leave the function, as soon as you don't have any callbacks, as soon as you don't do any await, the minimum snippet of code you write is logically executed with exclusive access to this particular object. That's the plan so far. Keep in mind that following the Git flow analogy, the main branch may already be ahead of you. So you can do whatever you want, but then the merge might fail. But within your work, you have exclusive access, you're good to go, you're safe. So yeah, commits are atomic, these commits. And that's one of the biggest points of the talk, of the presentation. once you write your function, your business logic code, you can make modifications to any number of objects. It can be 0, can be 1, can be 1,000,000, but you can only do one commit. That's the design idea we're suggesting. So you have to commit everything at once. That's the first trick. So like you can do tons of branches, but you have to tie the knot. If it's a single data instance being modified, then it's kind of simple. If it's multiple data entities, well, the more conflict heavy operations there are, the more you load the framework. This is where loosely ordered queues come into play for you to be careful with contention factors. But you can try to modify tons of objects. Then you say commit, like on the code level, and either they all succeed or at least one failed. And if it fails, it's like an exception. You can catch it. But if you catch the exception, after this, you can no longer commit. You're not allowed to. It's going to be expensive, except into conflict-free data types, such as counters, login, or inserting into other loosely ordered queues. So your logic is, let's do this and this and this, and try to commit. Oh, it failed. All right, let's insert this command to the log-free loosely ordered queue, and we're done. On the next tick, we'll try this again. Or you could be, oh, I'm trying to commit for the third time, so the loosely ordered queue failed. Okay, fine. I'm going to push it to the different loosely ordered queue, which would actually lock this object entirely, and then try again. So that's a lot like in Linux for a long time now. There are no mutexes. To be precise, they're replaced by futexes. Futex stands for fast user space mutex. It's effectively mutexes in Linux are a little bit lock-free. If your contention factor is low, you would never ever go to the kernel. You would still use like a lock-free atomic operation on the object of the mutex, but only if a couple times. I think it does like 3 iterations with small busy waits, but only if this fails within like single digits, maybe dozens of instructions. Only if this fails, it goes to the kernel and says, I need access to this thing. Please add it to the kernel level queue. Once it's free, call me in my due turn. But it tries to do it without going to the kernel first. We're using the same idea. We're trying to let you commit everything. If it fails, that's why you need the kernel. In our case, the durable execution kernel that is logically unified, but physically lives across machines. I hope I'm not too fast. I mean, I'm pretty sure what I'm saying makes sense, but it could be heavy. From here it follows naturally that it would much like with async await programming, every single step between async await should be like order of 1-ish. So please do not scan large ranges because you will slow the framework down. If you potentially need to scan large ranges, you probably want to have some index data structure that keeps like the keys ordered in certain hierarchical structures. These are all minor details. The important part is that once you rethink all this, you would quickly see that the integration, the integration between schema and code becomes too tight. That if you want to do it as a framework for a given language, the instrumentation would be too expensive. That's why I think it should be a small, lightweight DSL, not a language itself, but something domain specific, super trivial. Yes, Alex.
I didn't get why each invocation of business logic code should take constant time. Do you mean like so constant time would be between branch until try to commit, try to merge, or?
No, so it's more like the term all of one here is a bit misleading. I take it. The idea is that it is expensive to keep multiple contexts in memory. Mm-hmm. Durable execution implies that whatever is running has to be running durably. So there is some distributed storage that stores the state of your function over a long period of time. So if you run something super expensive, it's just expensive for the framework to keep it. So whenever possible, make your data operations lightweight. Order of 1 just means you do not do like scan all users to find every user called Alex. in a hash map because the order is not deterministic. Like, please do not do that. That's just too expensive for the framework. That's it. Much like you don't do a large select on a production database. You want it to be OLTP light. Is it? I can expand further.
Yeah, please, because I think I still don't get it.
Let's take the async await green threads runtime as an example. The wait, why are green threads better than kernel threads? Well, because kernel threads are high overhead, both in RAM. They have their own stack, which is usually in megabytes, and in CPU cycles to get to the kernel and back, like protected mode, OS rings, and whatnot. Green threads, as soon as you can afford to use green threads, you're much faster. You can literally have millions of them because they're super lightweight. But each green thread that is running in production in your service, you still have this overhead, even though it's not small. It's a stack. It's a stackless function, but the stack is somewhere. It's like a stack emulation, so to speak, even though it's a real stack. But you still have some data blob in memory that keeps all the context of this asynchronous function. When we take it one step above, one step higher, and talk about durable execution, this context of this asynchronous function should now be saved in some storage that is shared by multiple nodes. So that if your machine is dead, or if your storage, if your data center is dead, it should be able to resume the same function from the same step. So if you start spinning up expensive functions, you can just overload the whole system, no matter how much money you throw at it. It will be embarrassing if you dedicate, 10,000 machines to your large-scale backend, and then some intern writes an expensive function that scans the entire set of users, and then somebody improvidently starts like refreshing the page, calling this function 1 million times, and then the whole service is down.
Okay, so what do you mean? You mean not like business logic will take constant time, but the fact that you should split your logic in such a small blobs, like that, so they would be relatively small and plus minus similar size, right?
Right.
Okay.
And
I
that's why
got
the
it.
gas
Thank
fees
you.
analogy makes so much sense. So like effectively think of yourself as paying for each CPU cycle. And there's just a hard limit. Ideally, the framework will just try to execute your code. I hope it's compiled, like just JIT compiled, not interpreted. But once it's been executed, it also keeps track of how many instructions it runs. And if it runs like more than a few thousand, it should probably stop, with an exception that your code is too slow. Like you try to do too many things. Ideally, if I put on my like academic hat, I would say, do not use let's limit the DSL to primitive recursive functions, where there's no halting problem, where you cannot possibly write the code that runs for an unbounded period of time. So you can prove, like static type, and LinkedIn can prove that this function is guaranteed to execute for no more than this many operations. Like you could go all the way there, which I would love to if I'm working on this for real for many years. But for now, let's just assume the framework will kill your function if it's taking too many cycles, not time, but cycles. And it's on you to design your functions, like to break it into smaller chunks if you need to. Cool. Thanks for the question. So now, when it comes to what actually runs this code, we like to think of this as a threefold solution. Of course, it can be run on-prem, as in on your physical machines, or if you just provision machines, EC2 or Hetzner, or that's pretty much if you have a use case when cloud is not acceptable for you, for instance, because it's private data and you don't trust cloud providers. Wherever you can claim you need some budget for consultants who would spin up a Kubernetes cluster for you, you can run this execution framework, this durable execution maroon functions, and be happy with that instead. That's probably the easiest to box down as a use case. Like this is something that can be hackathoned. Let's build this framework that executes some code on these 10 machines, where you run some binary, some Docker compose, doesn't matter. Option 2 is that this could be managed service, which is even more fun. So that you as the company owner, as a business owner who's using this, you have developers who write code in this framework, and you're just paying some big entity, think of AWS or Google Cloud or Azure, Oracle Cloud or whatnot. You just pay them per usage, like per stored unit, per compute unit, and they just elastically scale as needed. If you're super small, your bill is like $5 a month. If you keep growing, well, that's where private contracts come into play and you get some discount, not like millions, but hundreds of thousands. But I can see the world where once the DSL is mature enough and once the paradigm is mature enough, managed services would be preferable for large players who just need things to work. And of course, number 3, ideally, if all is done right, you could run this in a decentralized fashion. Everything's encrypted, both at edge and in transit. There's another slide on this. So you can run your own nodes for you can run your own nodes for your code only, but that's closer to point 1. You can run your own nodes to support some other people's code and storage, and you can even be paid for it in some tokens. It's a proper Web3 use case where all those machines warming up the planet because Bitcoin is warming up the planet, they can be used for good, and we could have like a Firebase available for everybody for pennies, and it's guaranteed to never go down because all this encryption and keys and hashes are working out their magic, which I think is a fantastic use case. It will be called, I can see it. The reason I love this problem is that on the one hand, it's super important. On the other hand, it's quite clear how to solve it in this common denominator setup. So I can see working on this in all 3 settings, and then this hider will have 3 hats. Which one goes first, enterprise, on-prem, or decentralized? Time will tell. But the DSL part, the execution part, the example code, the proofs, the linters, all of these components are totally independent of where this code is executed. A couple small things we need to talk about. So this slide captures a lot of things at the same time. So since we do have these global epochs controlled by this framework, they are not, the global epochs are above every single lineage of every single data singleton. It's like a global epoch number. And one idea that we like is that this global system can generate pseudo-random seeds per epoch. So that, imagine 10 times a second, you have 10 large UUIDs. Each epoch corresponds to its own UUID. That is pseudo-random, as then you cannot predict what the future ones would be. They're generated by the system. And then you can say that whatever requests users send to the system must be signed with this random seed as the key. What it gives you is that if you send a request, but you sign it from a minute or an hour ago, it's considered an old request. For you to send the request, for it to be processed, it has to be signed by one of the last 30, so last 3 seconds hashes. This is cool because of 2 things. Number 2, the less important thing, is that for the system to be properly idempotent, it must return the same response for the same request. Which means that you can send the same request that you sent a year ago, and the system must respond with the same response as a year ago. But if you know from the request approximately when it came, you know right away at the load balancer level that this one is really old. So route to the OLAP, not OLTP. Route to the slower database. Maybe go to disk. That's okay. As long as it does not interfere with the critical path, we're happy. That's advantage number 2. Advantage number 1 is that you can pick this signing function to be cryptographically expensive to sign, but cheap to verify. At which case, the system immediately becomes resistant to DDoS attacks, distributed denial of service, because sending this system traffic becomes a far more expensive task than filtering it. So if you really want it to be running like a decentralized setting, all you need to say is, you know what, your request from the browser will always take another 0.15 seconds, which is almost unnoticeable for the user, but that's immediately making it super cheap for the backend to be protected from bad actor attacks, which I believe is the future. It's, in a way, it's already the case with Web 3. Let's just bring this into Web 2-ish product. closing notes. There are a few slides left, but we're almost there. So, of course, behind the scenes, for this to work, we have some distributed consensus. The actual implementation at the lowest possible level may well leverage the native means available. For instance, if you want to run this on, let's say, Amazon has its own means to provide consensus. Actually, Amazon is not the best example. Google here would be a better example. You can use Google PubSub, which is quite cheap for messages, and suddenly you do not need to worry about order. The cloud provider does it for you. That's another topic of mine that is dear to my heart, but we don't have much time to go into that. Consensus is expensive. Consensus is hard to build, right? So please do not write your own Raft. People have done it before. But the beautiful part of the consensus problem is that once you have built or have access to a slow and expensive consensus, you can use it to build a fast and inexpensive consensus on top of it. Because the slow consensus would only kick in if your machines die. You can say, I have 100 machines, I dedicate these 5 to be providing my local consensus, and these 5, when they need to agree among themselves if one of them is dead, that's why you take the expensive call to your cloud provider. But this expensive call would happen once a year. It's just a mechanism to guarantee that you would not screw it up. And then your own fast, cheap consensus is what powers your system. That's effectively how this partial order vector clock lineages of these individual data singletons and their perpetual slides, that's how they are managed. And another big closing note is that, thanks Alex for your questions, we do need to have some storage layers, right, to store the state. But the beautiful part is that storage is cheap these days. You only need to make sure you do not need too much from it. And S3 grade AWS storage, where you just store large blobs and hope they are there. That's super cheap these days. So, and once we have properly built layer to execute durable functions, most state would be in memory across multiple machines and multiple regions. So snapshots are infrequent, and this magic does not require too much money from the runner. And S3 grade storage is super cheap these days, and it's also available from tons of providers, including open source solutions, including like Hetzner has its own S3 that is cheaper than Amazon by a factor of 10, not to mention Web3 great solutions that offer S3 compatible storage. Yeah, so we talked about this before because, again, thank you for good questions, but business logic code is stored within the system, as in with the schema, because version upgrades are organic, no need to go into more detail. We want to point out that this is effectively the superset of event sourcing, because if you do this thing correctly, the stream of events effectively is produced as a byproduct. So it's very easy to imagine that you just declare some durable executed maroon function, maroon fiber, as exposed to the world, and it's just available for the outer world through some Kafka stream, because it's very organically created by the system. And encryption is so easy to introduce. You can do at rest and transit, bring your own key. BYOK is the modern day hot topic because people want to be super safe. Understandably so. That's 2024. And yeah, since our custom execution framework is first-class citizen from day one, because we are considering this cell phone-based, browser-based, Web3 grade decentralized execution, it has to be encrypted, and it comes very, very naturally how to encrypt stuff. It's going to be slightly more expensive, but that's the price we pay. Last but not least, testing is so clean with this framework because you don't need to test any databases. You can trust, and you should trust the framework to perform distributed consensus, distributed execution, aggregations. So there's nothing that has to do with sagas, rollbacks, two-phase commits. It just happens for you correctly. All you need to do is to write some invariant, like test on invariance on business logic. The rest is taken care of for you. The test on high contention, test on peak throughput, that's a separate conversation. But again, you can write artificial tests on fake data and measure it. And that's what the team working on the framework itself should be happy to incorporate in their routinely run tests while they are working on better language and execution provider. tons and tons of use cases we can talk about. So any small business, I kept talking about Google Docs as an example because I like it, but literally Telegram, Slack, I don't know, payments, anything you use today, Notion, Airtable, can be built this way. Dear to my heart is the example of orchestrating production deployments. So if you ever use stuff like Chef or Puppet or Ansible, it's a pain if something fails in the middle, like midway. Well, with this framework, it does not fail. It just runs. Any non-trivial task queues. Task queue is actually a difficult problem by itself, almost insolvable. Once you have task queues where you need some priorities, extra conditions, what fires after what's periodical, that's expensive and tricky, but with this framework, it happens magically. Any legacy data systems that cannot be befriended. When Alex sends Bob something, but you need to first confirm Alex has this to be sent to Bob, and then suddenly, because your company acquired some other company, Alice's tokens, excuse me, Alice's tokens are stored in Postgre, and Bob lives in Mongo, and that's just pain, unless you use a durable execution framework that can do the magic for you. Well, Firebase is my favorite example. Cheap Firebase for everybody that cannot be turned off is, I think, a natural extension of these ideas turned into decentralized use cases. And yeah, massive state machines at scale. I think it's one of the canonical examples for products such as Temporal. If you think of the Uber Eats order, how would you design Uber Eats? You have maybe not millions, although yeah, millions sounds right. You have millions of concurrent orders. Each order has its own non-trivial state machine. You need the restaurant to approve it. You need them to confirm they can cook it. Eventually, you're being told, like your service is being told, hey, this order is almost done. Let's schedule a driver to pick it up in 5, 6, 7 minutes. The proper driver is selected, maybe making multiple stops along the way. Then the driver needs to deliver the orders to people. All this is just large-scale orchestration and literally nothing else. And you need to make sure you do not lose orders. So either you have tons of rollback and state restore logic, or you use the durable execution framework. Just a few slides left, I promise. Internally, we have this orchestrator. I like this idea of meta-consensus. I sort of talked about this briefly when it comes to building cheap consensus on top of expensive ones. So that's probably going to happen, especially in the setting where one system orchestrates multiple businesses domains at the same time. Like you can build Google Docs and you can also build Gmail in the same space, in the same realm. Could be the same machines that run it, but they're totally separated. Like logical data universes are totally separated. The way to run it effectively, that's where the black magic starts. I assume the DSL will be JIT compiled into low-level code, and a lot of optimizations have to be built in, have to be used. For instance, obviously in the critical path, what should be linearized 100%, one after the other. There's nothing to do with strings. There's nothing to do with like string manipulation. Obviously, don't parse JSONs there or create JSONs there or protobufs if it's binary or whatnot. This all happens outside the main thread, so to speak. And outside the main thread, you can have multiple workers, like multi-thread environments. Good engineers know how to do it. It's not too difficult. It's too much fun, and it's super effective. So the innermost loop can literally do tens of millions of operations per second, if not more, if you prepare the data carefully. And because you do this, you can also be careful enough to make sure that even though the logical memory space is literally terabytes, petabytes large, you have this conveyor, like on a CPU level conveyor belt. So you can do prefetching of like preparing future instructions. At the same time, you can also prefetch the data into your own local legitimately used caches, so that if you need some data in memory, it's going to be warm for you by the time you need to execute this. So it's fast and it's durable. You can push code to data on the orchestrator level, on the executor level, but you can also, even if you fail to push the code to the right data node, it's still prepared for this code. The critical path part of the code does not have to wait until the data is stored from memory or from disk or from a different machine. It's just there by the time this code is run. So yeah, all this JSONs and stuff. I'd love to talk about this, but certainly not today. That's too much of implementation details. So yeah, I think we had this slide before. It's just a recap. version of your branching, like Git analogy, optimistic locking, try to not lock anything unless absolutely necessary, and for as long as you can do things without locking, just uproll it, Web3 term, into the main branch, and you're good to go. Functional programming, pure code, no side effects, no machine dependencies, including contract resolution code for potential automatic merging, so to speak. And the OOP idea is that every single object, singleton, data singleton, effectively has its own small queue next to it, which is a CQRS command query responsibility segregation style command queue for this object. PS, number one, we don't have a well-chosen name for this, so if you have good ideas, welcome to Slack or Discord. And number two, mini announcement. We want to have this, we have this idea of Kaggle for SysDesign, and we have a well-designed problem statement for a key value store under this artificially constrained environment, which in a way can be viewed as halfway to this durable execution framework problem. So if you are curious, well, we don't have DSL specs yet. This key value store problem is well postulated, and hopefully you'll enjoy that too. I think that's all I had. Any questions?
Yeah. First, thank you. Second, I know, is it fair to say this, but I had a vague suspicion that I was told about EVM kinda system. Is it fair to say like this, or
EVM?
like Ethereum virtual machine?
Oh,
Ethereum virtual machine. I mean, maybe just it's just too late for me right now, and it's a bit hard to assess on the spot, but at least so many concepts were quite similar or very similar. Yeah, maybe you can comment on this.
Yeah, I can be super brief, partly because it's late for you. Vitalik started Ethereum specifically when he realized the logic that blockchain nodes can execute does not have to be limited to a specific task, such as prevent double spending in case of Bitcoin. So what Vitalik did is he said, every single node, every single transaction cannot just be something of a predetermined hard-coded set of commands, such as send tokens from Alice to Bob, but any Turing-complete program that is going to be interpreted by this node according to the rules of this Ethereum virtual machine. The language of Solidity was designed specifically to write this code. But I'm not a close follower of Ethereum. I think right now when they have L2s, it may end proper uprolls. I'm not sure how well distributed across these partial order vector clock dimensions these things are. From my understanding, it's not meant to solve the problem we're talking about right now. Like you could build your own Slack or Firebase on EVM, but it's going to be like it's still going to be in the dollars per transaction in fees. But it's not that we're trying to present the way to bring Web3 ideas into Web2. It's quite the contrary. We're trying to claim that we know enough as the industry. We know enough both academically and pragmatically to have a unified language to define data singletons, data objects, and their mutation rules, to enable developers to not have to think about persistence at all, while still writing effective, provably correct code. If it ever runs in a Web3 setting, you probably will not even touch EVM at all because you can do better. These days, I mean, it's not a Web3 episode, but we can talk more about modern ways to build consensus engines that are cheap and effective, but that's not the point. The point is that if you have 20 machines to run something, I would much rather have you run 20 binaries, like 20 identical binaries, configure them to point to one another, and that's your durable execution cluster with no EVM ideas built in whatsoever. If you can phrase your question in a more narrow way, I can probably have a better answer.
No, I can't. No.
It's not like
But
another way to look at it. Go on.
no. I just want to say I think I kind of got it, but I probably need to think about it tomorrow.
Another way to think about it, which is another bet I lost, not 10 years bet I lost, but I think I'm close to almost winning it within like 15, 20 years, is the boundary between software developers and DBAs. So if you use a SQL database, an RDBMS, if you're a big company that needs hundreds of machines, if not thousands of machines to run like a proper database, there's a dedicated role, database administrator, DBA, whose job is effectively to look at the queries, find the most expensive ones, introduce indexes on the fly by means of injecting code into the Ryan database. Sometimes fake counters to optimize query execution paths so that the database would make wrong assumptions on which tables are larger in order for the tail latency to be better. So there's an extra layer of black magic on how to optimize the storage layers. So people can write code, but the storage layer is optimized by other people for production to remain stable. And I keep saying that this separation has to change. Like, we no longer live in the world where it's even feasible to have a company that runs 1,000 machines database and employs like 7 full-time DBAs whose job is to see which indexes can be hacked away to optimize the internal query performance. And if you think about the problem in this way, let developers write business logic code in simple logical statements, and let the job of the DBA to be, oh, you need this index here, you need this reverse lookup, I'll have you this index. I'll have it for you encoded in the type signature of this object, but your business logic stays the same. And I see this world clearly, but I have not done enough homework to articulate it well. Maybe by examples it will be better eventually. That's my point, is that imagine your data query sometimes is like, give me top 5, like the scoreboard, top 5 users from this country by rating in this online game. If you do this in SQL, you can later create index in this database. If you do it in EVM, in Solidity, on the Ethereum blockchain, you cannot change the code of this EVM code to assume you now have this index. There's no way to create the index. You need to change the code to assume some blockchain indexer created the index that you need, or you build your own component from scratch to do this indexing, like to put all these per country ratings into some skip lists to perform this operation quickly. So that's a lot of that. That's exactly the legacy we're trying to get rid of. If you have a single system, same piece of code with some DBA level optimizations on the data structures level, gives you the correct results. If you have an expensive, large-scale system, you create legacy that is difficult to work with 10 years later. Shall we? Alrighty. Thanks, gents. Let's call it. Talk to you soon.